Welcome to the first lecture of metal mediated synthesis 1. Well, in this first class, we will be discussing mainly the asymmetric version of the hydrogenation reaction. I am sure that all of you are familiar with the hydrogenation reaction. Essentially, we are talking about starting with an olefin, converting that olefin into an alkane, or you start with ketone, you get an alcohol. So, this is addition of hydrogen or 2 hydride across an olefinic center or an alkyne or even a ketone center. The mechanism of this reaction can vary a little bit based on the organometallic intermediate that is involved into these reactions. One of the best hydrogenation catalyst is the Strock-Osbourne catalyst. Now, we will first look at the mechanism of this Strock-Osbourne catalyst, and then we will discuss only one example to shed light into the asymmetric hydrogenation reaction. Let us look at the Strock-Osbourne catalyst and its mechanism. First of all, we would, for example, we would like to have these asymmetric reactions mainly to synthesize a number of drug molecules such as Lipitor, which is a multi-billion drug, one of the best selling drug presently in the market, something like $100+ billion is earned on this. This is a drug marketed by Pfizer, and then of course nowadays a number of generic versions are available. In India it is known as, let us say, Atarvedal, also in the name of Lipitor. Now, this drug Lipitor, if you look at carefully, there is 2 asymmetric centers. These asymmetric centers in principle or in reality also are generated by the hydrogenation reaction. Well, before getting into the asymmetric hydrogenation, let us draw the drug Lipitor and then look perhaps how can it be synthesized by asymmetric hydrogenation. So, the Lipitor. So, it has 2 stereogenic centers. It is a rather big molecule, as you can see. Well, you can do a number of ways to synthesize this compound. Now, most importantly, as you can see, these are the 2 stereocenters that perhaps can be generated by asymmetric synthesis. Of course, you can think of a diketo center at these 2 carbon centers and then do an asymmetric hydrogenation to come up with these centers that will effectively give you the desired molecule. As I said, before getting into the details of these drug molecule synthesis, let us try to look at the catalytic cycle, which is the fundamental of these hydrogenation reaction. Catalytic cycles will vary based on the catalyst, also sometimes based on the substrate that is involved for the hydrogenation reaction. Today, only one catalyst system we will discuss, and that is Strock-Osbourne catalyst. So, Strock-Osbourne catalyst mechanism. Well, it is a rhodium based catalyst. It is a rhodium bisphosphine complex, which is now a 12 electron species. Initially, of course, this 12 electron catalytic species is generated from a pre-catalyst where it is a 16 electrons complex. Usually we have a olefin coordinated, 2 of them rhodium species that is commercially available along with 2 phosphine ligand bound with it, and it is a cationic species. The anion X minus usually are the non-coordinating one, that is for example BF4 minus and PF6 minus. This is your rhodium catalyst. Now, this rhodium catalyst is commercially available and known as the Osbourne catalyst. The phosphine ligands, these ligands can vary. The olefin we usually see it's a bis coordinated one, for example cyclooctadiene or norbornadiene. This is NBD, norbornadiene. Cyclooctadiene can also be used for these reactions. The species that we look at here is a 16 electron complex. Now, this species will undergo the hydrogenation of the internal olefin itself, that is coordinated with rhodium, to give rise to the alkane as well as the reactive intermediate, that is going to be now a 12 electron intermediate. From this 12 electron intermediate we will start our catalytic cycle. These internal olefin which are bicoordinated such as norbornadiene or cyclooctadiene are sacrificial olefin. Since it is a hydrogenation catalyst itself, the rhodium one, it will be efficiently hydrogenating the internal olefin to give norbornane and and corresponding alkane compound for whatever we have as a bidentate ligand. Now, from these sacrificial ligand which is providing the support for the pre-catalyst, we will get a very reactive 12 electron species coordinated by just 2 phosphines. These phosphine coordinated rhodium complex will now be the real active species for the catalytic cycle. Let us look at that. Okay, now we have the rhodium bisphosphine complex. The counter anion that is involved in these cases are BF4 minus or PF6 minus, which is giving enough opportunity for the rhodium center to be catalytically very active, and subsequently we will see the major reactions that is happening at this rhodium center. In these cases, binding of olefin takes place with the rhodium center to give you the rhodium olefinic complex, cationic one and bisphosphine coordinated one. This was a 12 electron species. Now, upon olefin binding it becomes a 14 electron species. From here oxidative addition with hydrogen occurs. So, these are hydrogenation reaction. You start with an olefin as a substrate and hydrogen as the other substrate. Olefin coordination occur first. This is a Osbourne catalyst we are discussing, and then with hydrogen oxidative addition happened and it was found to be the rate determining steps. We see the hydride formation, dihydride formation. These are dihydride catalyst. It is not the monohydride catalyst which we see in other cases where one of the hydride is associated usually in the commercial form. Metal monohydride species is taken and from there catalytic cycle start. In these cases we do not have a monohydride to start with into the organometallic intermediate or the metal complexes. Here we have a vacant coordination site, a number of vacant coordination sites at the metal center, then olefin bind and then oxidative addition into the hydrogen happens to give you the olefin coordinated dihydride intermediate. From here we have the beta migratory insertions. I hope you guys are all familiar with it. I am not getting into the details of it, where you see that at the beta position, alpha beta position, these hydrides are getting in, and of course your 2 phosphine ligands comes into the picture. Finally, reductive elimination gives you the product where this hydride and this whole alkane now gets eliminated to give you the final product. In this catalytic cycle, therefore, you have seen starting with olefin coordinated organometallic intermediate and with a non-coordinating anion, the catalyst that is known as Osbourne catalyst will gives rise to a reactive intermediate wherein olefin is now no longer part of the metal catalyst. We have a very reactive 16 electron species to a 12 electron species formation by the loss of those 2 olefin, which is a sacrificial olefin going to the alkane product, but our major reaction is an exogenous olefin reacting with hydrogen, where with that 12 electron species olefin coordination occurs. Subsequently, we do see oxidative addition, that is the rate determining step in these cases usually, to give rise to the dihydride catalyst, rhodium dihydride species with olefin coordinated one, from which we have seen a beta migratory insertion to give the metal hydride and alkyl species. The final step is the hydride and alkyl group beta or reductive elimination to give you the product formation, and it regenerates the catalytic cycle. I am sure you are familiar with these processes. Now, the major topic for our discussion is how these hydrogenation catalyst can be used for asymmetric reaction. For example, if those phosphine ligand that we were discussing in Stock Osbourne catalyst are having stereo center, phosphine having stereo center, can they give rise to a stereo center into the product? Of course, the answer is yes. Asymmetric version of the hydrogenation catalyst are quite popular. So, today we will see 1 or 2 particular examples where asymmetric hydrogenation reaction is taking place. Let us look at one such example. All right, let us look at one of the substrate, and that is aspartame synthesis could be the sweetener, famous sweetener or similar type of synthesis. Let us look at one of these where you have an acid and an NHCOMe. These are the 2 coordinating group, but the major interest, our major interest is at this olefin. We want an alkane formation or saturation of this unsaturated partner to give you the stereo center in this particular case. The catalyst that will be used is the rhodium dicoordinated ligand complex. Of course, this is a chiral ligand and you have a cationics complex. We use hydrogen to give overall a species that is going to be very interesting for asymmetric reaction. Okay. So, we are just putting phenyl over there. Now, the ligand, this ligand that is used in this case are the bisphosphine ligand, where you have this phosphine center having the chiral ligand center, and this aryl group, for example, this is a phenyl, this is a phenyl, these 2 are aryl. This aryl group could be like orthomethoxy1, initial partner and so on. Well, if we have the amine instead of phosphine in these cases, these ligands are not going to be asymmetric, or these are not going to be chiral center, because as you know, the inversion energy or the inversion barrier required for the amine is pretty low, which is achievable at room temperature, but for phosphine asymmetric ligand synthesis or enantioselective catalysis is possible with the phosphine ligand, because we can make the chiral version of the phosphine ligand, and this is one of the ligand that is used for these cases. Okay. Now, let us look at the mechanism of these reactions. Of course, we also know that since the ligand is having chiral center, with respect to the ligand we can bind the olefin in 2 fashions, which is leading to the 2 products, 2 stereo center containing product. One would be the R product from the starting material, another would be the S product from the starting material. Now, we will try to discuss what is getting generated and how it is generated, what would be the mechanism of such reaction. Let us look at the product formation for these 2 cases and the possible stereo center generation steps that will require then a rhodium complex with chiral ligand. With respect to that chiral ligand, now the substrate will be oriented in a way so that in one conformation it can give you the R product, hydrogenated product. The substrate can also orient in another way where it is leading to the S product. Now, from there on we will see what is the experimental observation and how that can be explained further in detail. Okay. Now, we are going to draw a catalytic cycle or semi-catalytic cycle. We are assuming that phosphine ligand is rhodium PP and we are giving a star over there, and we are going to have, let us say, initially a solvent coordinated species, which is usually the case, and we are going to take the substrate which is the one which we have discussed in the last slide. So, we have CO2OMe and NHCOMe. Now, in these cases, in this particular case, as we have drawn, we are getting overall the final product as the S product, right. So, the product from the hydrogenation of these reactions we are getting is the S product that I am trying to draw in here, NHCOMe. So, essentially this olefin double bond is now getting hydrogenated. One of the hydride is coming over here, another hydride is coming over there. So, this is the S product and that is turned out to be the major product. This is the major product. The other product is the minor one or very little one, since it is a very good asymmetric reaction, and that is the S product, and that we are going to draw right now. This is the one where the mirror image of this one, we essentially have drawn the mirror image of that one, and that is the S product, and this is the R product, and that is the minor product. Okay. Now, the catalytic cycle which we have drawn for the Stock-Osbourne catalyst is also valid in here, where we have seen bis coordinated phosphine ligand, in this case asymmetric version of the ligand, will be interacting with the metal center, and you have an olefin associated with it. We will also see the dihydride species formation from the oxidative addition of hydrogen. From there on, a beta migratory insertion into the olefin will take place, where hydride attacks the olefin. Now, this mode of olefin binding will determine whether this is going to be an R product or S product, and the mode of olefin binding will be in turn related or governed by the chirality of the ligand center or the substituent having the proper steric configuration or steric demand will force the olefin to bind in only one manner. But what in this case, in particular case, we were seeing is selective S product formation. But if you look at the mechanism of this reaction, intermediate isolation indicates that intermediate that can be characterized should lead to the R product. So, let us look at the scenarios in hand. Two different product is possible, one is the S product, another is the R product. The reaction mechanism study for this reaction indicates that intermediate that is forming or that can be characterized are similar or should lead to the R product, but in reality we are getting S product. The question is how that is possible when R product intermediate is characterized, but the product in reality we are getting is S. Let us draw the mechanism, or let us draw the corresponding intermediate. The intermediate that was characterized is having this phosphine ligand, and where we have seen that the olefin is coordinated in a fashion, we have NH over there and then we have COMe, and from this side CO2Me is attached. So, this is the olefin coordination. Olefin is coordinated and you have a phenyl over there and CO2 Me over this side and the ketone, that is NHCO Me, that is associated with the rhodium in this fashion. Now, this one in principle should lead to the R product. This is the only observed intermediate, but the product that we see is the S1. The corresponding intermediate, let us draw it over here, is not really going to give us the desired product, but in reality this is what we are getting in the process. I will show you the intermediate in a moment where I have already drawn it, and that would be little bit clear, and from here this is the intermediate that is getting generated and the product being formed. Let us look at the intermediate in little bit clearer way. If you can see over here, well, let us look at this intermediate in a little bit better drawn fashion, because drawing over here with the pen is becoming little bit critical. Let us look at this in a pre-drawn manner, which I have done before from the original reference that has been given that has been published earlier. Let us look at this rhodium intermediate, where your rhodium is having this chiral ligand and solvent coordinated. From there on, this olefin can coordinate with this rhodium center in two fashion, as is drawn here in the form of 16 double prime. On the other hand, the 16 prime, as you can see on the left hand side, is the intermediate that is only observed. The 16 double prime intermediate is never observed, whereas the only observed intermediate is 16 prime. This 16 prime intermediate is not leading to the corresponding compound, that is 23 in this case, but this is observed as the minor product. So, the intermediate 16 prime is observed intermediate only, 16 double prime is never observed, but the product formation is not governed by the 16 prime. Original product formation is actually governed by 16 double prime. So, this is somewhat little bit confusing, but this can be explained by what is known as Curtin-Hammett principle. Let us look at the Curtin-Hammett principle, and then we will try to come back to this problem again and discuss it further. So, Curtin-Hammett principle tells you that from one reaction, if you are expecting two different conformer or two different intermediate, so your starting material are going to give you two different intermediate. If these two different intermediate formations are not going to be very much energy demanding, that means they can be in equilibrium or one can go back to the other one very easily. Under that condition, the product formation step from those two intermediate will be determined by the next transition state coming out from them. Okay. Let us look at this phenomenon one more time in the form of this energy diagram. Okay. Let us look at the energy diagram. You have A and B, two intermediate, A and B, two intermediates that are in equilibrium with each other. Okay. Now, from intermediate A, product C is forming, and from intermediate B, product D is forming. If you look at the relative energy from intermediate A, this TS1 is the shorter one, whereas from intermediate B, the product that is D forming, that intermediate and that product formation energy or energy barrier is quite high. So, delta G1 over here is smaller, delta G2 over here is larger. So, this is smaller, this is larger. This is a small part and this is a large part. Now, although you see that A is having higher energy, B is having lower energy, if these two are intermediates, you will usually see the formation of B only from the reaction mixture. So, the characterization of intermediate in this particular case is going to be the B. You will may be able to isolate or characterize B because A is having higher energy, but from A the product formation is of lower energy, but from B product formation is having higher energy. So, in this reaction mixture, although A is having higher energy, B is having lower energy, overall the product formation actually going to be C, not D. Okay. That is because if A and B are interconvertible, they can be formed in equilibrium. Under that situation, and this energy barrier is very less, and therefore, under that situation B can always go back to A, and then A to C product formation, that is the lower energy formation compared to lower energy requirement compared to the subsequent B to D formation. So, intermediate characterization can sometimes be misleading. Maybe it is indicating the other product formation if it is under the Curtin-Hammett principle. So, what we have seen here in this particular energy diagram is A and B, although are in equilibrium, B is having lower energy. So, you will be able to characterize B, but the product formation is actually observed finally from A, because A to product formation C is much facile compared to the B to D formation. So, this is what essentially is the Curtin-Hammett principle, where the equilibrium between the two intermediate can be determining the product control step, and that is the one which is having the lower energy. Irrespective of the energy between the two product formation steps, as long as A to B transition is smaller, we will see always the product formation C. Let us get back to the original this hydrogenation catalyst one, where we will see that starting from this rhodium complex, we have this 16 prime and 16 double prime possible formation. We only in the reaction mixture we see 16 prime, but we are not going to see the product formation 23 in this case. This is turned out to be the minor product, because from 16 prime to 23 is a higher energy, relatively higher energy steps, whereas from 16 double prime to 24 is a lower energy steps compared to 16 prime to 23. So, 16 prime will be converted to 16 double prime, and then 16 double prime is going to give you the product formation. This is what roughly is the Curtin-Hammett principle, where equilibrium in terms of the intermediate will be the key factor, whereas the corresponding transition state will dictate the term which intermediate should give you the product formation. The characterization of one intermediate does not necessarily mean that that intermediate will form the product. In some cases, this intermediate can be converted to a further lower energy intermediate. In this case, it is happening, and therefore, we further even the higher energy intermediate case can be possible, and from there product formation, as long as is favorable, we will be ending up seeing it. So, what we have seen in this class then, asymmetric hydrogenation is quite a powerful technique. We might will not be discussing too much of asymmetric hydrogenation anymore. So, idea simply is, if you have an olefin and you have the hydrogenation reaction, if there is a possibility of generating a stereocenter, the stereocenter can be controlled by the ligand on the metal center. Of course, you need a stereocenter at least in the ligand. It could be 2 stereocenter in the ligand. Overall, an asymmetric hydrogenation reaction is an extremely powerful technique for synthesizing a number of valuable drug molecules. One of those is the levodopa. From here, we can see that this hydrogenation reaction is now really applied in industrial scale to give a number of value added product, which are often the drug molecule presently in the market. So, in the next class, we will be discussing not the hydrogenation reaction anymore, but we will be getting into the carbene reaction. So, you can study about the asymmetric hydrogenation in detail. Due to the shortage of time and the overall syllabus coverage, we will be mainly focusing on the carbene reaction from here on, and after that we will be getting into the cross coupling reactions, namely carbon-carbon, carbon-nitrogen, carbon-oxygen and carbon other heteroatom bond formation reaction, also various other organometallic reactions where metal plays a crucial role. Without the metal center and the organometallic intermediate, the synthesis would not have been possible, and literally there is no other alternative that is available for such catalytic reaction or for such bond formation. So, we will discuss more on that in the next class. Till then, keep studying. Maybe let us look at the asymmetric hydrogenation little bit into the detail. First look at the hydrogenation mechanism, and after that try to look at some of the examples of the asymmetric hydrogenation reaction. Well, till then, see you. Bye bye.